Okay, so let us start. In this session, our aim is to prove the Radon-Nikodym theorem and Lebesgue decomposition. As I had mentioned earlier, this is a beautiful proof due to John von Neumann, which proves both the Lebesgue decomposition and the Radon-Nikodym theorem in one go. Okay, so let us start. So, proof of the Lebesgue Radon-Nikodym theorem. Okay, so let us recall the statement of the theorem. So, it had two parts. So, given a positive sigma finite measure, right, both are important, and a complex measure, lambda is a complex measure, I have first a decomposition, right. So, that is the absolute continuous part and the singular part, and the absolute continuous part is given by a Radon-Nikodym derivative. Okay. So, these two things we have to prove. Okay. So, in the proof, so let us just write it down. Mu is the sigma finite positive measure, right, positive measure, and lambda is complex. Okay. And we need to decompose lambda with respect to mu and also find the Radon-Nikodym derivative for the absolutely continuous part. Okay. So, first assume that lambda is positive. So, if lambda is positive, since it is a complex measure, it is also finite, right. So, it is a positive finite measure. So, this kind of reductions you have seen several times when we dealt with functions. You can always assume function is positive, prove it, and then prove it for real valued functions and then for complex valued functions. That is precisely what we are going to do now. Okay. So, let w be the function constructed earlier, the function constructed earlier. What was the property of this w? Well, this was strictly between 0 and 1, okay, and w was in L1 of mu. More importantly, if I integrate w over e and I get 0, that will happen if and only if mu of e is 0, right. So, this was the property we needed. Now, using this w, we define another measure. Okay. So, define. So, first we will write this in the symbolic form. Okay. So, d phi equal to d lambda plus w d mu. Okay. So, this is in the symbolic form. So, I'll explain what this means in just a moment. Well, it should mean whatever is written here, and it should obviously suggest something, right. So, what does this suggest? This suggests that if I integrate over e with respect to d phi, then I should get it to be integral over e with respect to this measure on the right hand side, right, but that is d lambda plus integral over e w d mu, right. So, this is the meaning of this identity. Okay. So, I am defining a new measure phi, right. So, phi is a new measure defined. Well, what does this mean? This means that phi of e equal to lambda of e. So, lambda is our given positive finite measure, right. We are assuming that it is a finite measure, plus integral over e w d mu. We know that this also defines a measure, right. W is in L1. So, that is also a finite measure. Okay. So, hence I am adding two finite measures, hence phi is a positive finite measure. Okay. But phi dominates lambda, right, because this is positive. So, this is positive, and so when I am adding positive things to lambda. Okay. So, so lambda is actually less than or equal to phi. Okay. At any set, this is going to be true. Okay. So, from this, so let me write this in a slightly more familiar fashion. So I can write this as indicator of E d phi, right. So it's not theta, it is phi. That is the left hand side. Right hand side is integral over x chi E d lambda and integral over x chi E w d mu. So w d mu you can view as one measure if you like. So if something is true for indicator functions, we will immediately get that it is true for symbol functions, right. So this immediately implies integral over x s d phi equal to integral over x s d lambda plus integral over x s w d mu for every simple function, simple positive function f, positive function s, right. So it's a positive simple function, okay. But then you can apply monotone convergence theorem. So MCT, apply MCT. So we'll get well, what do? You take any positive function, choose Sn simple functions increasing to it, and you will have convergence everywhere, right. So on the left hand side you will have convergence to f d phi. Right hand side, because d lambda is a measure, so that will also converge to f d lambda plus this w d mu is another measure, and so apply monotone convergence theorem there as well. So you will get f d. So for every f positive, measurable of course, okay. Alright, so keep this in mind. This is something which we have to use several times, okay. Alright, so that is the relation between phi and, so maybe I can write it down here again, d phi is written as d lambda plus w d mu. Okay, so next consider T of f, okay. So T of f, so you have seen that this is going to be a linear functional. Well, I should give you a definition. So this is integral over x f d lambda for f in L2 of phi. So remember the measure phi, lambda and mu. So now there are three measures. Mu is the positive given positive sigma finite measure. We transferred it to w d mu, so that is a finite measure. Lambda is assumed to be positive and finite, right. So phi is something which dominates both lambda and w d mu, okay. So I take f in L2 phi and I define integral over x f d lambda as Tf. Of course, I don't know if it is finite, etc. We'll prove that. Well, let's do that. So integral over x f d lambda, okay. Take the modulus inside, mod f d lambda. I want to say this is finite, right. This is of course less than or equal to integral over x mod f d phi, right, because if f is positive, so mod f is what is here, so that is a positive quantity. This is positive quantity, so you are adding a positive quantity. So this guy here will be greater than the integral with respect to lambda. Now phi is a positive measure, so I can apply Holder's inequality or Cauchy-Schwarz inequality to get mod f square d phi to the half integral over x. So I'm taking mod f to be mod f times the constant function 1, okay. So 1 square w d mu, sorry, d phi, because I am applying Cauchy-Schwarz inequality to d phi to the half, right. So that is the Cauchy-Schwarz inequality or Holder's inequality, Holder's with p equal to 2, right. Well, so the right hand side, so what happens to this? Well, this is the L2 norm of f, right. So with respect to the phi measure times 1 square is 1, so I have the total measure of x to the half, but this is a finite quantity, right. It's a finite measure because you are adding two finite measures, right. So here, so this is a finite measure, okay. So what did we prove? We proved that the expression for Tf, which is the integral over x f d lambda, so modulus of Tf is less than or equal to some finite constant C. So, this is a finite constant times L2 phi norm, right. So, this is true for every f in L2 phi, that is what we have proved. So, that says T is continuous. Okay. So, this implies that T from L2 of phi, so it is a finite quantity, right. T makes sense, T is a map from L2 of phi to the complex plane. It is of course linear. Well, what is T? T after all is simply an integral, right. Tf is equal to integral over x f with d lambda, not with phi, remember that. It is a linear map of course, and it is continuous. Why is it continuous? Because of this inequality. Let us see why it is continuous. So, if Fn converges to f in the domain in L2 of phi, right, then I look at Tfn minus Tf. I want to say this goes to 0 in the complex plane, right. That is what continuity means. But T is linear, so T of Fn minus Tf is Tfn minus f, right. But now I can apply this inequality. So, this is less than or equal to some constant which is finite. It has nothing to do with f, right. So, the constant here is independent of f, that is important. Okay. So, I have some constant here which is independent of f times Fn minus f, the L2 phi norm, right. That is what we have here. But this is what which goes to 0 because Fn converges to f in L2 phi. That means Tfn converges to Tf. So, T is continuous. So, continuity part is true. So, now we can use our result. Well, what is the result? If I have a continuous linear map on some L2 space, then that is given by an inner product, right. So, there exists a unique G in L2 of phi such that T of f equal to integral over x f, well, instead of g bar I will simply write g d phi, okay. That is what we have, correct. So, you can think of g bar as the function, so that g bar bar is g. So, we will have this, but what is Tf? So, recall that is integral over x f with respect to lambda, okay, no, not phi, okay. So, now let's not bother about what is in the middle. So, we will simply write in this. So, what we have is integral over x f d lambda is equal to integral over x f g d phi. What is g? G is the unique function in L2 of phi which defines the linear functional on the left hand side, okay. So, remember this equality, we will need that. Okay, so let us start with, so we need to understand what is G a little bit more, okay. So, put f equal to indicator function of E, okay, with phi of E is a measure, right, positive, okay. Phi is a measure, I am looking at a set E such that phi of E is positive and use this, okay. So, let's call this star, okay. So, in star you put f equal to chi, that is allowed, right, because that is in L2. So, well, so this is true for every f in L2 phi. G is a unique function in L2 phi, right. Okay. So, if I put f equal to chi e which is in L2, then I will get, what do I get on the left hand side? That is lambda of E. On the right hand side I will get integral over E, because it is chi e, right, f is chi e, g d phi, okay, g d phi. So, which is positive of course, right. So, this is greater than or equal to 0. So, if I divide by phi e, so 0 less than or equal to lambda e by phi e equal to 1 by phi e integral over E g d phi, right. These are averages of G with respect to the measure phi which is finite, right. But what do I know about lambda E by phi E? That is less than or equal to 1, right. Lambda E is less than or equal to phi E. Phi E is bigger than lambda, right. So, this is less than or equal to 1, the quotient, and so the averages of the function g are between 0 and 1. Okay. So, now you can recall what we have done earlier, right. So, hence averages of g belong to the closed interval 0 1, which is a closed set in the complex plane, and so by our result, right, and so by previous results g itself takes values inside 0 1. So, g of x is in 0 1 almost everywhere x with respect to the measure phi, right. Remember, g is in L2 phi. So, I have the space x and I have some set here, and g of x here is between 0 and 1. Okay. This set has measure 0 with respect to phi, right. So, if I call E, it is measure 0, and outside that set it has it is between 0 and 1. So, here I will simply put g to be 1 or 0, 1 constant. Okay. So, remember, the space need not be complete. So, you can't define g to be arbitrarily there. So, redefine g so that 0 less than or equal to g of x less than or equal to 1 for every x in x. Okay. So, I can define g to be just 1 here, and then we are done. Okay. So, we assume it for all x. Now let us go back to, so we have some information on g. Okay. So, now let us use this again. Okay, star. So, what does star say? Star says that integral over x f d lambda, that was our TF, that is equal to integral over x f g d phi. G is the function in L2 phi, right. But d phi, what was d phi? D phi is d lambda plus w d mu, right. So, I put that in. So, this is equal to integral over x f times g d lambda plus integral over x f g w d mu, right. So, I am just using this summation. Now, there are lambda integrals on the left hand side and the right hand side. So, bring it together and recall that g is between 0 and 1. Okay. So, I will get integral over x 1 minus g f d lambda, okay, equal to integral over x f g w d mu. Okay. So, this is another identity which we will use again and again. Okay, let us call that star 2 stars. Okay. So, now comes the magic of von Neumann. So, here he decomposes the space. Okay. So, put the set A to be all those points x. So, now everything is controlled by g. G is going to be g will give us the Radon coordinate derivative and the decomposition. Okay. So, all those points x such that 0 less than or equal to g of x strictly less than 1. Okay. So, pay attention to the strict inequality, and B equal to the set where g is actually equal to 1. So, remember, we define g to be 1 on a set of measure 0. So, it does not really the A and B will differ at whatever definition you take. A and B will differ at most by sets of measure 0. So, it is not going to change anything in the integrals. Alright. So, you have A and B. So, what do you know about A and B? A union B is the whole space, A intersection B is empty, right. Okay. Now, define. So, this gives you the first result. Define lambda sub A of E. So, I am trying to give you the expression for the absolute continuous part of lambda, right. So, that is lambda, that is where G is strictly less than 1. So, that is A intersection E, and I have the singular part where G is 1. This is lambda of B intersection E. Okay. So, lambda A is concentrated on, so this tells me lambda A is concentrated on A, right, and lambda S is concentrated in B, right. So, the definitions itself says that they are concentrated on A and B, but A and B are disjoint. Okay. So, that immediately implies that they are mutually orthogonal to each other, I mean mutually singular, right. So, lambda A is singular with respect to lambda S. Okay. All right. So, now if I take f equal to indicator function of B. So, what is B? B is the place where G is equal to 1 and put this in. So, put f equal to chi B in star star. Star star is this, right. So, if I put f equal to chi B, what do I get? So, let me write one line integral over x 1 minus G chi B d lambda equal to integral over x chi B G W d mu. Okay. What does this say? This says that, well, what is B? B is where G is 1, right. So, G is 1. So, 1 minus G times chi B, this is equal to 0. So, the left hand side is 0, right hand side is on B G is 1. So, chi B times G is 1. Okay. So, I have integral over, well, chi B times G is chi B. So, integral over B W d mu. So, with respect to W d mu, the set B has measure 0, but then we know that this immediately implies mu of B is also 0, right. That was one of the results we mentioned when W was constructed, right. W d mu and d mu will have same 0 sets. So, mu B is 0. What does that mean? Lambda S is concentrated in B and mu of B is 0. So, that means these two are mutually singular. So, lambda S is mutually singular to mu. So, this was one of the things, and we need to show that lambda A is absolutely continuous with respect to mu. Okay. So, that is the last part of the proof. So, this is another new idea will come here. So, replace f by 1 plus g square plus etc plus g to the n times chi E. Well, what is E? E is set f, okay, in so we used star star for that. Okay. So, in star star, right. So, star star I will write down again so that it is clear, in star star. So, what was star star? So, star star, let us denote it, write it down here again. So, that was integral over x 1 minus G f d lambda equal to integral over x f G W d mu. Okay. So, I am replacing f by this. So, that is allowed because this is true for all f in L2 of phi. Phi is a finite measure, G is bounded, right. So, G is less than or equal to 1. So, all these quantities are less than, all these functions are less than or equal to 1. So, it will add up to some finite finite bounded function. So, I can replace f by this. Well, what will I get then? I have the whole summation here times 1 minus G, that will give me 1 minus G to the n. Well, let's take n minus 1 here, so that I get 1 minus G to the n d lambda, right, over the set E, because there is a chi E, right. So, let us, instead of x I will write E, okay, because f I am replacing f by this whole thing, correct. Okay. So, equal to, on the right hand side f is replaced by, so chi E is there, so integral will become over E, f is replaced by this summation times G W d mu, right. So, G into 1 plus G square plus etc G to the n minus 1 times W d mu, right. So, we have this. Now, let n go to infinity, So let n go to infinity. If n goes to infinity, what happens to the left hand side? Well, this converges to lambda of A intersection E. Well, why is that? Because what was A? A is the set where G is strictly less than 1. B is the set where G is 1, right. So I can write E as E intersection A union E intersection B. So the integral splits, and on E intersection B this is 0 because G is 1. On E intersection A, G is strictly less than 1. So G to the n will go to 0, right. So apply dCt whatever you want, and this is by definition the lambda A of E, correct. Lambda A of E by definition is lambda of A intersection E. So the left hand side converges to what we want. What happens to the right hand side? Well, this is a increasing sequence because G is positive and you are adding each time, right. So increasing, and so you multiply by W, you will have an increasing sequence of functions converging to something. So converging to, let us say, H, okay. So H will be positive, and by monotone convergence theorem, so by MCT, this converges to integral over E H d mu, okay. So what is H? H is the limit of G times 1 plus G, G square, etc., G to the n minus 1 times W, right. So I can write that explicitly if you want. H equal to limit of G into 1 plus G square plus etc., G to the n minus 1 into W d mu, okay. Well, if you write this as G into G by 1 minus G times W d mu, you will see what is actually happening. Whenever G is 1, this G by 1 minus G into W is infinite. That is the singular part, okay. That is what the set B captures. That is the singular part, because this is what behaves like the Radon-Nikodym derivative, right. So whenever G is 1, the Radon-Nikodym derivative is infinity. So that part gives you the singular part, remaining gives you absolutely continuous part, okay. So if I write this separately, what we have just proved is lambda A of E is integral over E H d mu, right. And so this of course, and if I put E equal to x, I know lambda of A of x. So this is a finite quantity because lambda is assumed to be a finite measure. Lambda of x is finite, so lambda of Ax plus lambda s of x is finite, and this is equal to integral over H d mu, right. So this is finite implies H is in L1 because H is positive, right. So H is in L1, okay. So now we have proved all that we want, right. So let me recall that again, and then we will conclude with some remarks, okay. So what did we prove? We have lambda positive finite, okay, mu positive sigma finite. Then I can write lambda equal to lambda A plus lambda s, right. Lambda A is absolutely continuous with respect to mu. Lambda s is mutually singular with respect to mu, and lambda A can be written as, so lambda A of E can be written as integral over E H d mu, where H is a positive function because we have positive lambda, and H is in L1 mu, okay. So if you want, so in symbols, so Radon-Nikodym derivative of lambda A with respect to mu, right. So this is H, right, that is the symbol we have, or in other words d lambda A. So we already used this notation H d mu, right. That is what this equality means, okay. So sometimes symbolically we will write like this. So H is the Radon-Nikodym derivative. Okay, so the proof is not yet complete because we assume that lambda is positive and finite, Okay. So next thing is to assume. So next assume that lambda is real, okay, real valued, right, instead of complex valued. So that is what we called signed measures. Okay. Then we can define lambda plus to be lambda plus mod lambda by 2. We have done this before, and lambda minus equal to mod lambda minus lambda divided by 2. Okay. Then both lambda plus and lambda minus are positive finite measures. Okay. So the theorem applies. So I can write lambda plus as lambda plus the absolute continuous part plus lambda plus the singular part, right. Similarly lambda minus also will have, right. So lambda is given by, that is a real measure. So that is lambda plus minus lambda minus. So when I subtract, I am going to get the difference of two absolutely continuous measures, which is also absolutely continuous, and difference of two mutually singular measures with respect to mu. So that will still be mutually singular with respect to mu, right. So for real ones the result will follow from positive ones, and for complex ones it will follow from real ones, right. For complex lambda, for complex measures lambda, write lambda equal to lambda 1 plus I lambda 2, right, where lambda 1 and lambda 2 are real measures, are real valued measures. And for this we have decomposition, for lambda 2 we have decomposition. So just like what we did here, we will get a decomposition for lambda as well. Okay, so that part is easy. So going from positive finite to complex measures is like what we do with functions. From positive functions you go to real valued functions, and then from there to complex valued functions. Okay, so one remark, we can do the same, if lambda is a positive measure. Okay, positive measure, maybe sigma finite, let's put sigma finite measure. That means, but the Radon-Nikodyn derivative, but h equal to, let us say, d lambda by d mu need not be in L1, of mu. Okay, so what do I mean by this? So let's take two sigma finite measures, and we have X as our space. Okay, now mu is sigma finite, mu is the given positive sigma finite measure. Okay, so that decomposes X into various pieces, right. So x1 I have x2, I have x3, x4, etc. Now in each of them I can restrict everything to xn. So if I take xn, I have mu of xn finite, okay, and lambda of xn finite. So I can decompose it, because both are sigma finite measures, right. So I can decompose it x such that both of them are finite, and so in each xn I will have a decomposition, right. So on each xn, lambda admits decomposition with respect to mu. Okay, and then I can add up, right. Adding up will give me decomposition of lambda with respect to mu. Only thing is you will have the Radon-Nikodyn derivatives, right. You will have h4, h3, h2, h1, etc. They are all in L1 in those spaces, but over the whole space X it may not be in L1. Okay, so the Radon-Nikodyn derivative, so the Rn derivative of lambda with, or lambda a with respect to mu need not be in L1 of mu, but it will be in L1 Radon-Nikodym derivative, let us call that H, but H will be in L1 locally. Okay, what does that mean? Integral over H d mu will be finite for every n, okay, for every n. So, in each of these components you have L1ness, but put together it will not be. So, let us see a trivial example to see why this is true. So, let us take mu to be the Lebesgue measure on R, okay, and lambda is the positive sigma finite measure, right. So, I will take it to be 2 times the Lebesgue measure, okay. So, m is the Lebesgue measure on R. So, of course, lambda is absolutely continuous with respect to mu, right. Whenever mu of E equal to 0, lambda is 2 times mu. So, obviously, lambda of E is also 0. So, restricted to any compact set, I should be able to get a Radon-Nikodym derivative, which is the constant function 2. Okay. So, d mu by d lambda, if you look at, is actually 2, okay, which is not in L1 of mu. Okay, not in, because L1 of mu is L1 of R, right. R has finite, infinite measures. So, constant functions are not there, but if I restrict it to any set which has finite measure, it will be there. So, this completes the proof of the Radon-Nikodym theorem. Okay, we will stop here. Okay, so we just saw the proof of Radon-Nikodym theorem. First, we did the proof for positive finite measures lambda, and as usual we extend it to the real measures and complex measures. And the same proof works for 2 sigma finite positive measures mu and lambda, and you can get a Radon-Nikodym derivative which need not be in the L1 globally, but it is L1 locally. Okay, so that is what you should understand. Now, from next session onwards, we will see various consequences of the Radon-Nikodym theorem. There are quite a lot of interesting consequences, some of them we will see that. Okay, we will stop here.